conduct, we have partially filled conduction band. So we have conduction band with free electrons there that can move, okay, and they are the only moving charge in the metal. So the semiconductor is very, very interesting because it has both free electrons and free holes. So it has two types of free carriers, and that is what makes it extremely important, for device applications. And again, let's clean a little bit here. So what we try to say, at low temperatures, the valence electrons are bound within the covalent bonds. That is to say, they are in the valence band. So these are called bound electrons, i.e., that is to say, they're bound to the atoms, attached to the atoms. They are unavailable for conduction. That is at very low temperatures or at absolute zero. In the terms of the energy band picture, these are what we call the valence electrons, which cannot move. They are the electrons in the valence band. And so they fill up the valence band. When the temperature is increased, thermal vibrations may break the covalent bonds. Thermal vibrations give energy to the electrons, and therefore the electrons become energized and they can break away from the bonds. So they can become free electrons. So that free electron can move with the applied voltage and create a current. In other words, we call it conduction electron. Similarly, we have an electron deficiency in the bond now, which is in the covalent bond, that makes a positive charge in that region, and these deficient bonds or deficient electrons can also move, as we saw, and we call them holes, right? So these deficient electrons are called holes, okay, and they're able to move. So these electron deficiencies from one bond to another require a supply of energy to the crystal lattice, okay, and these covalent bonds are energetically indistinguishable. They are the same. An electron can easily jump from a bond to another bond if it has a hole, okay. So this electron deficiency is a free particle, right? But this free particle is called a hole, and this hole has a positive charge of 1.6 times 10 to minus 19. So holes are free to move and they have a positive charge. Where do they exist? They exist in the valence band, as I told you. You have free electrons in the conduction band, free holes in the valence band. So the electronic device and the conduction in the electronic device is actually governed by the free electrons in the conduction band and the free holes in the valence band. Okay? So let's go back, just quickly look at this picture here and clean it. Okay? And then if we look at it, every electron, free electron, leaves behind a free hole. Every free electron leaves behind a free hole. Every free electron leaves behind a free hole. So in this semiconductor, which has only silicon, very pure semiconductor, only silicon, and if you increase the temperature, you get the number of free electrons exactly equal to the number of free holes. This is called intrinsic semiconductor. Intrinsic meaning it's only self, it's very clean. It has nothing but silicon, nothing but the semiconducting atom, or the elemental atom for the semiconductor, like silicon or germanium and that. So these are called intrinsic semiconductors, okay? And so in an intrinsic semiconductor, look, the word intrinsic now shows up. You can see the word intrinsic here. In an intrinsic semiconductor, your concentration of electrons is exactly equal to the concentration of holes. So, at finite temperatures and at continuous thermal agitations, energy is given to the electrons, and so the electrons are able to move from the valence band to the conduction band, right? So that is something that we have, and leave behind holes in the valence band. An intrinsic semiconductor is the one that contains relatively small amounts of impurities, no impurities, very pure semiconductor. But in reality or in practice, it's impossible to have zero impurities. You would always have some background impurities. So that is why we say it's impossible to create a semiconductor with no impurities. But if you have very small little impurities, then you call your semiconductor intrinsic. Okay? So the conduction in an intrinsic semiconductor is equally shared by free electrons and free holes, which are supposed to be of the same concentrations. So the electron density, so how do we now figure out what's the electron density at any temperature? Okay, so what I'm going to think of a model like this. This is your valence band, okay, and this is my conduction band, okay, and this is my energy gap between these two, okay. So this is my energy gap here, and what I'm going to do, this is the energy axis, so it's one axis, which is the energy axis. So I will go to some energy in the conduction band here and call this energy a variable energy E, okay? So that this distance is energy E, and then I take a very small infinitesimal increase to E plus dE. So I'm going to use a little bit of calculus. So I take a region in the conduction band of energy region E to E plus dE. Okay? Now, I want to calculate the number of free electrons per unit volume in this range. So the number of electrons per unit volume in this range of energy, I'm going to call it dNE. That is the number of electrons per unit volume in the energy range E to E plus dE, energy range from E to E plus dE. What does it equal to? It's equal to the number of states. Now this is a little bit of statistics. The number of electronic states that are available here to be filled by the electrons per unit volume in this region. So this is called the energy state density, okay, which is energy states density, okay, is the number of electronic states in the energy range E to E plus dE. If I multiply it by the energy range, so it's the energy density, which is the energy per unit volume per unit energy. So if I multiply it by the width in energy, so this together with D gives me the total energy states for electrons to occupy in the range E to E plus dE. This one here is what we call the occupation probability, or the probability of occupying these energy states. So how do you calculate the number of electrons per unit volume in the energy range E to E plus dE? It's the total number, it's the density of states per unit volume per unit energy, which is GE, okay, multiplied by the energy width from E to E plus dE. So that gives you the total number of energy states per unit volume in this energy range. Then you multiply it by the probability that the energy state is occupied, is filled by an electron. Okay? Remember, here we're talking about millions, billions, zillions of electrons. So we have to use the statistics. It's like chairs, you know, we have 10 chairs. And then these chairs, we have, say, 100 students, right? We want the students to sit on these chairs. So let's say we have 2 chairs per unit volume, you know, per unit energy. So that is, if you want the total number of chairs, and if we have a volume of 5, then 2 times 5, right, times an energy range. So each chair has an energy range, we multiply by energy, and then we let the people occupy these chairs. The probability of occupation of the chair, maybe one of the chairs is broken, so the probability that a student will occupy that chair is only 1/4. Maybe one chair looks very fancy and nice, the probability of filling that chair is 1, so everybody will run to fill the chair with 1. That's the occupation probability. And everybody will try to move away from that broken chair, which has a low probability. So you have to multiply the total number of energy states per unit volume times the probability of occupation of the energy states. So this gives you the total number of electrons in the energy range E to E plus dE. Okay? So now, if we want the total number of electrons in the conduction band as a whole, so what we have to do is to go from the limits of the conduction band. Here is the limit, the lower limit of the conduction band, which is EC, the energy EC, all the way to the end of the conduction band. For simplicity, the top of the conduction band, we will call it E top. So here what we have is the number of electrons in this energy range E to E plus dE. If we want the total number of electrons per unit volume in the conduction band, then we have to integrate from EC to E top, which is the top of the conduction band. And this is what you get here. The total number of electrons per unit volume, N, that's the density of free electrons. These are electrons in the conduction band, so we're talking about free electrons, is equal to Dn, that's the number of electrons per unit volume in the energy range E to D to E plus dA, and then you integrate that from the bottom of the conduction band all the way to the top of the conduction band. Now, there are lots of statistical mechanics and quantum mechanics model that give me an expression for GE. Expression for GE, okay, is provided by quantum mechanics, and it includes this here, right? So this is my GE. This and all of this is my GE function. Here is my G function. That is the number of electrons per unit volume per unit energy in the conduction band energy states. And then this part here, okay, of course, together with just we have 1 on top, 1 over this is my occupation probability. So this is my F of E, that is the probability that a state is occupied, and this is my G, that is the density, okay, per unit volume, per unit energy. And what's the variable? I'm going to vary E, okay, which is here, here, and here, from the bottom of the conduction band all the way to the top of the conduction band. This EC is the bottom of the conduction band, so it's a constant. This EF is another constant. We will see it has a lot of significance. M star N is the effective mass for the electron in the solid. Kb is Boltzmann constant. Okay? T is temperature. Boltzmann constant is an important constant in physics, okay, and it has a value. I think we probably saw it before, but it's always a given constant that comes from a statistical physics, and it governs the statistics of occupation and how carriers move. So this is a very, very complicated integral, and it's very difficult to do analytically, right? And to simplify this integral and make it meaningful, be able to solve it, we have to do some assumptions. We have to impose some assumptions. So what we'll do is we will let the conduction band top goes to infinity. So we will assume, since we don't have any band other, the conduction band is the top band, so let's make energy goes all the way to infinity. Okay? Why are we doing that? Do we have physics basis for that? Probably not much, but it makes the mathematics easy. Okay? Make our measure of energy to be the bottom of the conduction band. So our reference in energy, we can move it to the bottom of the conduction band. So make the bottom of the conduction band 0. Set it equal to 0. That makes the integration easier. And later on, after we get the value of the integration, move it back to EC. Okay? So if we do that, then this integral suddenly becomes an easier version, like what you see here. Okay? Still it's very difficult, to figure out, because you have an e to power half here, and you have an exponential with an e down here. So it's still difficult to solve, but we can make an assumption. Okay? We are probably talking about high temperature because we said everything happens when we increase the temperature. So let's do another trick. Let us make the assumption that E minus EF, right? Let's make the assumption that this E minus EF is, something that is maybe much, so E minus EF energy, make it much larger than 3 kBT. So we choose temperatures that are not very high temperature, and that is true even around room temperature. Temperatures around room temperature, you still get this assumption. So what is happening is we're trying to do something about this exponential here, make it a little bit easier. So we're saying this numerator is very much higher than this denominator. We're assuming that. So if we do this, then 1 plus exponential here, this one becomes so trivially small compared to the exponential, because this is much larger than this. So this function here, which is in the denominator of the integral, becomes simply an exponential, okay, function, simple function like this. And that is, if you look back, that would eliminate this one. And so the exponential, we would divide by the exponential, so you just take it up, and you have a minus sign in front of this bracket. So, and that's exactly what you have here. So e to half exponential minus. You see the minus sign, so you brought it up in the denominator. Now you do the substitution, integration by substitution. You change the variable to an x, and then your integral dummy dx becomes dE over kBt, and then your integral becomes this simple integral here, x half e to minus x dx, and everything here can be taken out, all the constants out, including temperature, which is not a function of energy. And so what you get here, this is missing pi here. The integral simply gives you this result. Remember, here we're making the reference for temperature EC to be equal to 0. Now, what we're going to do is to go back to EC instead of 0. So instead of EF, we're going to write EF with respect to C. Okay, so instead of EF minus 0, it's going to be EF minus C, right? So we change this, the reference here, back to EC. So EF minus 0 becomes EF minus EC. So this is now your free electron density, free electrons in the conduction band. It depends on the effective mass of the electron. It depends on Boltzmann constant, which is a constant. It depends on temperature. This is Planck's constant, again temperature, and this parameter EF, okay, and EC. EF is a very important parameter, and we will see how important this parameter, which appears in the statistics. This is called Fermi level, and Fermi level, it's after a physicist who's called Fermi, and Fermi is the one who came up with the statistics, the occupation probability for filling the states, and that's why this constant takes his name. So now this concentration, free concentration of electrons in the valence band or in the conduction band or the conduction electrons can be alternatively written as N in terms of a NC, which is a function of temperature. So NC is this here, this prefactor, we're calling it NC, and this is called the effective density of states in the conduction band. At room temperature, 300 Kelvin, and if we take silicon, NC comes out to be 2.8 times 10 to 19 per cubic centimeter. For gallium arsenide, NC turns out to be 4.7 times 10 to 17 per cubic centimeter. So these are simply, when you evaluate, you put in all these parameters at room temperature, T equals 300 Kelvin, KB, it's 8.6 times 10 to minus 5 electron volts per Kelvin. M star is the effective mass of the electrons. H bar is Schrodinger equation. H bar is Planck's constant. When you put all these values for silicon, you get this. When you put it for gallium arsenide at room temperature, you get this. Similarly, doing the same analysis as we did for free electrons, we can also do a similar analysis to free holes in the valence band, and their concentration is P. N for electrons, because electrons are negatively charged, so we call them N, concentration is N. Holes are positively charged, so their concentration is P, which is for positive. We get the same thing, except now we have EV, that's the top of the valence band. So what matters to us is the bottom of the conduction band energy, which we call it EC, and the top of the valence band energy, which we call it EV, and the band gap. These are the three parameters in energy that we care about when we talk about a crystalline solid, semiconductor. So again, here you see the top of the valence band, because holes sit in the valence band, and again you get the Fermi level, the same thing, but now here you get the effective mass for holes, right? M star P. P always for holes, N always for electrons. And again, you can write this pre-exponential factor, you call it NV, which is this one, and this is called the effective density of states now in the valence band. This one is in the conduction band, that's why you see C here. This one in the valence band, that's why you get a V here. And again, at room temperature, NV for silicon is 1.04 times 10 to 19 per cubic centimeters. That's the effective density of states in the valence band. And NV equals 7 times 10 to 18 per cubic centimeter for gallium arsenide. So now we will stop here and then take something like 10 minutes break, and then we come and continue maybe for another half an hour.